Uh, Hello everyone. First of all, I would like to thank the scientific organizing committee for giving me this opportunity. So, although this talk is in the solar and heliospheric session, but I think it is much more general topic and of use for the overall MWA MWA science interest. So I will talk mostly about calibrating the instrumental polarization at meter wavelengths, particularly low frequencies, using unpolarized sky, and I will demonstrate with the MWA observations that this method is successful. So here is the team that worked on this work. Me, then Shurajit Mandal at NGIT, Angelos Vuli, that's my supervisor at Johns Hopkins, and several other students at NCRTFR and our SHI chair, Divya Baroy. So here is the brief outline of my talk. So first I will give you a polarization calibration recap to set up the stage, then talk about mainly the challenges of the low frequency polarimetry. Then I will describe the formalism that the main key part of this talk, and then how we apply those on the MWA data, shows the results, how much it is successful, and then end up with the conclusion and what is the implications of this method for the SKLO calibration, for SKLO polarization calibration as well. And as I mentioned, although this work has been started with some motivation for solar studies and heliospheric studies, the main motivation is to measure the Faraday rotation of the coronal mass ejections that you have heard already. And these are magnetized structures. So if we can measure the Faraday rotation induced by these structures, we can predict or estimate the magnetic fields remotely using the ground-based observations. But as I said, this method is much more general and applicable for any polarization science case. So why we need polarization calibration? The simple answer is that radio instruments are intrinsically polarized and also have its own polarization impurity. So whatever we observed is a combination of the true polarization of the celestial source that we want to measure, plus also the instrumental polarization. And we need to separate the instrumental part to get this true polarization of the celestial source, and what is our main target and required for any kind of science case. So there are two ways to do this, solve this any calibration problem. I would say either you have a priori information from certain known sources with their flux density, spectra, and polarization property. That is a standard way people have used, like we use the polarized calibrator sources or flux density calibrator sources for calibrating our instrument. Or if we have a good instrumental model, that is also can be used for calibrating the instrument. And this particular work is much more focused on the second part, which is generally not very commonly used for most of the standard calibration approaches. But at the same time, I would say that only instrumental model is not sufficient. We also need some a priori information of the sky as well. So to give you a brief overview of how the instrumental polarization is induced in the measurement, I will refer to this figure. So this figure shows that when the electromagnetic wave, that is the radio wave, is coming, it can be separated into or decomposed into two orthogonally polarized components that I have represented here by E and EB. And if this is a polarized source, linearly polarized source, the Faraday rotation of the intervening medium or at the source, ionosphere, everything can rotate this polarization plane. And then we have our instrument on the ground. Now these instruments I have shown as two dipoles. Those are orthogonally polarized. and those have different beams on the sky. And what we measure is, what we are observing is through this beam. And this beam of the instrument is also polarized. And ultimately what we receive is the voltages from these two dipoles, which are converted, amplified, and other electron post chain conversions have been done, which I am referring to the instrumental part, instrumental polarization part, which we generally decompose into time and frequency variable part, that is gain, instrumental gain, and there is a mixing between the signal from the X and Y dipole that we generally represent by the leakage terms or D. Now, what these voltages that we have measured is actually is converted through this entire chain of these different effects. Those are represented by the Jones matrices. And when we correlate these two voltages, we effectively get and our visibility is, that is the primary measurement of any radio interferometer, that we can write in this form. Now we can rewrite this equation into a direction dependent and direction independent form. Here I am not considering the ionospheric part, only the instrumental part. Now in the instrumental part, the direction dependent part mostly come from the instrumental beam. And if I multiply my source, the sky model, with the instrumental beam, that I am representing by this term called apparent source visibility. And the rest of the instrumental terms are represented by this JP, which are the direction independent. And the main target for this calibration approach is to figure out what is this JP terms, that is the direction independent instrumental polarization, including the overall Jones matrix that includes the instrumental polarization as well as the other time frequency variation gain. Now the low frequency polarimetry has faced some problem, and to understand that, we need to understand how many degrees of freedom we have in this calibration problem. So there are all the different antennas have different Jones matrices, but we can normalize them. We just add a average Jones matrix and then add average Muller matrix that has about 16 real parameters. But not all of them are independent, because the measurement that we will get ultimately have to be real, and so there are some physical constants, and that reduce the degrees of freedom to 7 degrees of freedom. Now to solve the 7 degrees of freedom, what we need, one single polarization measurement from a single source give you the 4 Stokes parameter. Hence we need 3 linearly independent Stokes vector to solve all these 7 degrees of freedom. Now why we need to solve this 7 degrees of freedom or not, that certainly depends on our polarization, certainly depends on our science case. So to understand that, we want to know what are the effects of this 7 degrees of freedom, or what are these 7 degrees of freedom at all. So one of them is the flux density scale. So to do that, we need to know the source flux and spectra of some calibrator source that we generally use for doing the band pass and flux density calibration. Next 3 degrees of freedom are the Stokes I, that is total intensity to the other 3 Stokes leakages, and this can be calibrated using unpolarized source. Now if our science case is limited to the total polarized intensity and spectra, flux density spectra, we then unpolarized, simple unpolarized source, and we can calibrate 4 degrees of freedom. But there still remain 3 degrees of freedom, which are causing the mixing between Stokes Q, U, and V, that is effectively rotating your polarization vector in the pole vector space. It is not changing the intensity, polarized intensity, but it is changing effectively the polarization mixing between these 3 components. It also causes the linear polarization angle change, and also the mixing between linear polarization and circular polarization. Now if our science case needs to have this information, we need to solve these 3 degrees of freedom as well. So this is effectively the what I have just mentioned, that if I have a instrument unpolarized sky, when we are observing using the instrumental beam, our instrumental beam is polarized. So effectively what is our instrument is seeing is not the
you have 5 minutes. Sorry to interrupt.
Sure. So instrumental beam that causes the polarized sky, and those we call Stokes pole conversion and pole rotation, and this Stokes I to QUV mixing is called pole conversion, and these three pole rotation terms are causing mixing between three components. Now we can normalize our instrumental Jones matrices in this form in terms of an array average quantity, and this array average quantity can be do in a polar decomposition in terms of a Hermitian and another unitary component, and this unitary component is related to this rotation, and this Hermitian component is related to pole conversion. Now physically this pole rotation is caused by this geometric rotation. If your all dipoles are not aligned with the sky coordinate, that causes this geometric rotation. If your dipoles are not orthogonal exactly, that causes the ellipticity error, that is causing mixing Stokes Q and V. And the third one is the cross and phase. Now for full polarization calibration, we mainly need to solve the pole rotation, that is the main target. And in general, it is assumed that the cross and phase only need to be calibrated and other terms as 0. But I think we need to validate this assumption. So for that purpose, we developed this general formalism. So we primarily use the apparent sky model observed through the instrumental beam, that is the polarized sky model. And since we have multiple sources across the sky which are observed through different parts of the polarized beam, that provide more than 3 linearly independent Stokes vector sufficient for calibrating all 7 degrees of freedom. And we use this for calibrating these 4x4 Jones matrices, normalize them, and correct the visibilities using that to obtain this term, this VJK chord. And then using this VJK chord, we now solve this equation where UP is the pole rotation terms to solve all these pole rotation components. Now when we apply that on the MWA, till now we have determined all these pole rotation terms, but mainly to verify the assumptions commonly used, like the array average geometric rotation is 0, ellipticity error is 0, and only cross and phase is sufficient to solve for full polarization calibration. So this figure shows these bottom two lines are the geometric and ellipticity error, which are almost close to 0, and here these white and gray lines are showing the cross and phase when we are obtained from solving all these three components, and when we are solving only the cross and phase. So both of them are matching very well. So this verify this that the four that sure these two assumptions are exactly valid. Now advantage of this method is that we no need a polarized source, which is often lacking at the low frequency. Also, we no need to make spectropolarimetric images of that polarized source to estimate the cross and phase. So it is this method is now very computationally efficient. And also the daily calibrator fields we can use for full polar calibration, and no need to make any assumptions about the cross and phase stability. Now we verify this method with standardized method that people have used using the linear polarized sources, and if the cross and phase is corrected properly, Stokes V should be 0. So we have chosen a AGN which shows a linear polarization and in the southern lobe, and if the cross and phase is not corrected, we see significant circular polarization in the southern lobe. But if we corrected for the cross and phase, both the new method that we have developed and also the traditional method people have used, both shows that the Stokes V emission is almost 0. This verifies this method is valid and properly calibrate the cross and phase like the standardized method. And also this figure shows that we can also detect this linear polarization emission and with this method, and the circular polarization is 0. Now we also tested this time variability and beamformer pointing dependence of the cross and phase, because now we can use any day of regular observations of the calibrator field, and we found that cross and phase is not dependent on the beam pointing, which is quite expected. But from the time variability perspective, we found that it is most or less stable over few day time scale. But if we go in month or yearly time scale, it is not fixed. And in all of these cases, we have used a single reference antenna. So this tells that the assumption, if we make that the cross and phase is stable over a long time, that may cause a problem in our calibration. So here is the conclusion, that this technique uses the unpolarized sky and solve a long-standing problem in low frequency, that we lack the polarized sources, more efficient in terms of the computation. And although it is developed for MWA and applied on that, it is much more generic approach. It is also verified with the standard method people have used in past with the linear polarized sources. And I think the key implication for SKLO is that with the increased sensitivity, we require better calibration with less assumptions, like cross and phase is stable or other pole rotations are 0. And this method demonstrates that it's capable for doing that for low frequency instrument. But the good thing is that this needs very good instrumental beam model. So with that, I stop here, and you can take this paper for more details, and you can contact me if you have any detailed query. With that, I will stop here, and happy to take any questions. Thank you.
Thank you. A question? I don't know who first.
Hi, David Jody. It's Alec Thompson here. Good to see you. I had a question on the last point of your summary slide. Wanted to check my understanding, and then if you could elaborate. So on the accuracy of your beam models. So if I'm understanding correctly, you have to apply. Is it true that you have to apply your leakage beams to your sky model in order for your model prediction? And if so, what level of error in your beam models, to what degree does that affect the resulting calibration accuracy?
Yeah, good questions. Now, if you remember that we are calibrating the direction independent terms effectively. So the accuracy of that term crucially depend on what is the beam average. So you have multiple sources, and we know that the accuracy becomes less at the edges of the beam. Now, but that accuracy we don't actually cause any problem. But if we averaged over the entire beam, the averaged error on the entire beam or entire field of view, that causes the problem. Now, for this case, I found that for MWA, if it is more than 40-degree elevation pointing, the beam model accuracy the average beam model accuracy is about 2%. Now, that is we are assuming that this 2% accuracy in your beam model is sufficient, means will transfer in terms in the polarization calibration, and the hands-on quant numbers is that it transfers as a 1/2, so half of that beam model. If it is 2%, so your calibration accuracy will be the order of 1%. So this is a rough estimate.
Awesome, thank you.
I think there's just time for one more question by Natasha.
Hello, thank you for the nice talk. I remember we looked at doing this a few years ago, and I wondered if you ran into the same problem we did. That is, if you have a very bright calibrator source that is, off to the side slightly in the primary beam, so it's in a highly polarized part, we found there was a big difference in the calibration solutions that we recovered if you removed all of the tiles that had any dead dipoles. So you only had tiles that were as consistent as possible with the beam model, or whether you included tiles that had the occasional dead dipole. So, unfortunately, the dipoles do die, the amplifiers fade away occasionally. And so if you flag all of those tiles, you lose a lot of sensitivity. So I wondered if your method was perhaps more robust than what we were doing, which was quite simple, or whether you'd hit the same problem.
Yeah, so what I found is that if I use, for example, I'm using for the the prediction, the hyperdrive. Now, I think now with the hyperdrive, we can effectively use the heterogeneous configurations, like if the one dipole has the 15 or 14 dipoles on another, and others are 16. And it is true that if we use that information during our model prediction, your cross and phase estimation, whatever you have estimated the cross and phase and other stuff, and if you consider, okay, my all tiles are working fine, but in reality not, and if we apply this that cross and phase, we are seeing significant leakage in the Stokes V. So yeah, it is true that we have to take care of those dead dipoles during the model prediction. Otherwise, it is a problem. So the overall thing is that you need a good BRIM model for the reliably applying this method. Yeah.
Okay. Thank you very much. Thanks again to the speaker. Let's move on to the next one. Thank you. Okay, next one is Soham Day. We'll talk about first robust detection of linear polarization from metric solar radio bursts. So same, I will give you the 5 and 2 minutes, okay? In the mic.
I'm audible, right?
Thanks.
Yes. Yeah. And you can see my screen, right?
Yes, thanks.
Yeah. Okay,
Yes.
sure. Thank you. So I'll talk about our detection of linearly polarized emission from metric solar radio burst, and this is the first time that we have robustly detected linear polarization from solar radio burst. So starting with what is solar radio burst, I'll give a very brief introduction to it, as Divya has already introduced it very well. So these are bright transient features that you observe from the sun, and these are coherent emission mechanisms, as they have very high brightness temperature, and they are accepted to be coming from plasma emissions. So they are divided into different types based on the structures of the dynamic spectra, and these are 3 examples of different types: type 1, type 2, and type 3s. And most of the solar radio studies have been based on the dynamic spectra. And of course, we know that polarization study of this burst is very important, because there are many things that we have not proved in detail yet. So, for example, we don't have robust detection or estimate of what are the coronal magnetic fields, how they are changing, and so on. Even we can get greater insights into the emission mechanism with polarimetric studies, and polarimetric studies will help probe the coronal medium better, their inhomogeneity, and the propagation effect of the radio emission through the magnetized corona. But the key point here that I would like to highlight is that most of the polarimetric studies have been based on the dynamic spectra. So you get disintegrated polarimetric measurements. So you don't have morphological information, such so on. And this is because imaging and calibration of polarization calibration at low radio frequency is difficult. Devajit has already mentioned many of the challenges. I'd like to highlight it a bit again. So the first challenge is that at low radio frequencies, most of the sources are depolarized. So you might not have polarization calibrated during your observation. And then you have your ionospheric parallel rotation effects as well, which becomes very relevant at low radio frequencies. For large field of view aperture arrays like the MWA, oftentimes the daytime, you cannot use daytime calibrators, as they will be contaminated by solar flux. And for a large FOV instruments like MWA, there are large instrumental polarization and they are direction dependent. So all this imposes that you need a very precise polarization calibration. Otherwise, since the solar flux is so large, even a minute leakage can give rise to a spurious detection of polarized sources. So what most of the studies have done traditionally is that they assume that we should not observe any linear polarization at these low radio frequencies because of high Faraday depolarization. So as Devajit has already mentioned, we have developed and verified a calibration strategy, polarization calibration strategy, which uses the unpolarized sky model. And we don't assume that we should not observe any linear polarization from solar radio burst. So coming to the background, why this assumption was used for the last 5 decades is that there are very strong expectations from theory that you should not see any linear polarization at this low radio frequencies from solar radio bursts because of the high rotation measure that you expect from the solar corona, which is of the order of 10 to the power 5 radian per meter square. And even with say very small bandwidth, you will get that the linear polarization will be washed out and you will not detect a linear polarization. At 1960s and early 1970s, there were few claims of this detection of linear polarization, but in that case, the calibrations were not that great, and they were detecting various amount of linear polarization in many cases. But after 1970s, there were many reports of non-detections as well, and people they doubted the instrumental calibrations, and from expectations, they do not expect any linear polarization from this burst. So the general consensus became that these detections are spurious, and the common norm was that we should not expect any linear polarization. And it has become such that so people either discard if they see any say linear polarization signals, or they used it as a calibration mechanism such that to correct for Stokes V. Assuming Q and U should be 0. So here is an example, a study that was done with loafer. So this is again dynamic spectra based study, and they calibrated the Stokes V by assuming that U and Q should be 0. And this leads to an implicit bias in all the polarization studies so far, because you are assuming based on the expectation. So coming to the background, why we started looking at this to go against the norm and to look at for linear polarization is because we detected some signatures of linear polarization in the uncalibrated dynamic spectra itself. So this is from a data set from 2014, and we are studying them, and this is the dynamic spectra. This is on the left is the Stokes dynamic spectra, and on the right is the Stokes Q fraction. So it is indicated in percentage. And these are just 4 minutes of data at 15 megahertz in bandwidth. So a very small time range and frequency range. And what you see is that this Stokes Q, so this is Q by I written in percentage. So you see this kind of transient features in the dynamic spectra. So for at the small time scale and frequency scale, you can this instrumental effect should be constant across the small time scales and frequency scales, but we see this rapid variation across this dynamic spectra. So we started to reinvestigate if this assumption is indeed true all the time. And we carried out linear polarization for this study, and we found that morphologically, they are again different what you get in Stokes and Stokes in polarization intensity maps. So again, we expect the instrumental leakage to produce a polarization intensity map that will mimic the Stokes sources. But as you can see, these two images on the left is the Stokes image, on the right is the linear polarization intensity map. They are at the same time and same frequency. There was a type 3 radio burst happening. And what you see is that there are two structures that are present on the linear polarization intensity map, while there is only Gaussian type source type 3 source that is present in Stokes I. And these dashed lines represent the polarization angle. So this was surprising, and what was interesting is that if you go to a earlier time, you can see there are two sources. So there were two Neustrom sources present, and during the type 3 time as well, you see the signatures of the Neustrom sources here. But this assumption. And in UV, they are associated with these two active regions, these two neutron sources. So this assumption has been used for the last 5 decades. So what we wanted to investigate, if it is always the case, if it is happening for this particular case or many of the times. So, and to get more evidence, so we started an observation campaign where we did simultaneous observation with GMRT and MWA. Uh, and uh, uh, so and luckily, for one observation, we did find active emission from the from the sun, and this is the dynamic spectra with the MW and the GMRT. On the left is the MW dynamic spectra, and on the right is the UGMRT dynamic spectra. And you see these kind of noise-storm sources in the dynamic spectra. And this spike you see is a type 3 burst, which will come. I'll show the morphological structures later. And luckily in this event, so in the dynamic spectrum, you cannot see it because it is disintegrated. But if you make an image, you can see there are two noise storm sources, one on the eastern region of the sun and one on the western limb. And luckily, since there are two sources, we can compare GMRT and MWA images, and we can compare two sources at the same time. And the observations were done at overlapping frequency and simultaneously. And these are the results of the simultaneous observations with MWA and GMRT. So the upper panel shows the MWA observations and the lower panel shows the GMRT observations. The maps are Stokes maps, and these contours are the linear polarization intensity contours. So you can see here the eastern source has been plotted here and the western source has been plotted on the right, and you can see that we get signatures of linear polarization intensity for both MW and GMRT. And what is more important is that we get very consistent amount of linear polarization from both MW and GMRT. And these are within error bars.
5 minutes.
Yes, sure. Then what we made is that specially resolved dynamic spectra for the eastern and western sources to see the variation of this polarization intensity and fraction across time and frequency. So this is for the western source and this is for the eastern source. And this arrow marks the type 3 burst. And what you can see, the top pen is the Stokes and the second row is the fractional linear polarization map. And you can see there are different, the variations are different for the different sources. The variation across frequency and time, they are very different. And you get a maximum of more than 31% of linear polarization fraction, and our residual leakage was less than 2%. So we can account this linear polarization not to be instrumental, but is what is incident on the telescope. And if we look during the type 3 radio burst, we see the morphological structures in different Stokes parameter. So the top panel is the Stokes evolution of the type 3 source. So each panel, so here it goes into as a sequence of 0.5 second. And the rows are IQ, U, and V. What is more interesting is that in the Stokes Q, you see a very nice evolution. So the type 3 bars, the maximum was at this time range, 14.2. And you see that it evolves from being a positively polarized Stokes Q structure, becoming dipolar, and then it becomes a negatively polarized source. But interestingly, you don't see such kind of structures in Stokes Q. You see that it gets elongated. And this morphological difference is interesting and we don't really understand. But what it confirms is that this instrumental leakage, say from Stokes psi, you will not get this kind of structures. So what are the possible origin of linear polarization? So interestingly, this linear polarization, there have been multiple instances of detection of elliptical polarization from stellar radio burst. And there have been many theories that for UV sets, the Bastian et al., they have theorized that they can origin from due to reflection from overdense plasma region, and they showed that if the reflections happen at the Brewster angle, not at exactly at Brewster angle, but for a range of angle of incidence, you can get a a fairly large quantity of linearly polarized emission. And for the solar corona, we know that this kind of overdense plasma region exists. So this is a white light image, and you can see there are these density contrasts that are there. But we don't think that this is the most dominant mechanism for the generation of linear polarization for our case, because you see this rapid change within seconds in the morphological structure, and it becomes hard to understand why they will come originate if they are reflected from far away plasma dense regions. So the another idea is that they can, yes, thank you. So another idea is that they can be due to mode coupling uh, when the propagation vector is perpendicular to the magnetic field regions. And interestingly, to give a bit of context, so these solar radio bursts are theoretically expected to be very high circularly polarized. By observational wise, there is a discrepancy. They are often seen as the circular polarization to be low. And this has been attributed to mode coupling, which converts circular polarization to linear polarization. And the theory was that subsequently Faraday depolarization would vanish, it will erase that linearly polarized component. What I suspect is that this is one of the cases where you are actually seeing that evidence of mode coupling, and this linear polarization component is the component that wasn't depolarized. So to conclude, we revived a decade-old assumption that which was assumed for the last 50 years, that we should not expect any linear polarization and low radio frequencies. We had a robust detection, and we did that with simultaneous detection with two geographically distant radio telescope of different nature, the MWA and the UGMRT. And this provides a new observable to study the solar corona and its propagation effect. The Stokes Q and U can be used as a new parameter to understand them. And the implications are beyond the solar radio burst, because in flare stars, from stellar radio burst, you often see elliptically polarized emission, and they are also coherent emission mechanism, but they tends towards being ECMA. And one of the reasons is that you don't really, it was assumed that you do not see any linear polarization from the sun, which was plasma emission. So they are often guided by the learnings of the sun, and now we are seeing that you can indeed get linear polarization from solar radio emissions as well. So with that, I'll stop. Thank you, and I'll take questions.
Thank you, Soham. Any question? Comments? No? Maybe I have a question to clarify one thing, because I was a bit, I wasn't paying fully attention. You mentioned that some mutual coupling effects can affect your results? Or
No,
wave
so
mode coupling?
Wave
Okay.
mode
Can
coupling.
you please clarify this?
So it happens if you have a magnetic field and there is wave propagation through the plasma, and so you will have this splitting of extraordinary and ordinary wave mode. And if weak coupling is happening, then you will have this you will get different the amount of circular polarization that will happen after it passes through that region it will be different. So it can change sign of the circular polarization, and at a particular value of the magnetic field and the number density of the plasma, what you can get is that a significant of the circular polarization to be converted into linear polarization. The requirement is that you need the magnetic field should be perpendicular to the wave propagation.
Okay, thank you. I misunderstood. Thanks. Any other questions or comments? No? So let's thank the speaker again.
Thank you.